We are taught early in school that matter comes in three simple states: solid, liquid, and gas. Water flows, and rocks don't. But there is a class of materials that refuses to follow these rules. They are the rebels of the physical world. We call them non-Newtonian fluids. These are the liquids that fight back. Materials that can be a liquid 1 second and a solid the next, defying standard viscosity rules and our very intuition. To understand why they are non-Newtonian, we first have to understand what it means to be Newtonian. Sir Isaac Newton described how fluids behave. In his world, the world of Newtonian fluids, viscosity is constant. Viscosity is essentially a fluid's thickness or resistance to flow. Whether you pour water fast or slow, its thickness stays the same. Petrol, alcohol, and pure honey all obey Newton's law. Their flow doesn't change just because you push them harder. Let's visualize viscosity. Think of it as internal friction. A fluid with high viscosity, like cold honey, has a lot of internal friction and flows slowly. A fluid with low viscosity, like water, has very little friction and flows quickly. In a normal fluid, this property is stable. But in the world we are entering today, viscosity is a shapeshifter. Non-Newtonian fluids break the rule of stability. For these materials, viscosity is not a constant number. It is a variable that changes based on shear stress. Shear stress is just a fancy term for the force you apply, like stirring, squeezing, or hitting. These fluids can act like a solid under sudden force, or relax into a liquid when slowly moved. There isn't just one way to break the rules. We generally categorize these fluids into two main types based on how they react to stress. The first is shear thickening. These fluids get harder and thicker when you apply stress. The second type is shear thinning. These do the opposite. They get thinner and runnier when you apply stress. The most famous example of a shear thickening fluid is something you can make in your kitchen: Oobleck. It's a simple mixture of cornstarch and water. When left alone or moved slowly, it looks and acts like a creamy white liquid. You can pour it and it will pool in a bowl, but try to punch it and everything changes. To understand this, we need to look at the physics. We talk about shear stress versus shear rate. Shear stress is the force applied parallel to the surface, like your hand sliding across the top of the fluid. The shear rate is the speed at which the fluid layers move past each other. In a Newtonian fluid, these two rise together in a straight line. In Oobleck, the relationship is exponential. So, what is happening inside the fluid? Let's look at the mechanism: shear thickening. In its resting state, you have cornstarch particles suspended with thin water layer separating them. However, when you apply high shear stress, it squeezes water out. Particles lock, forming hydroclusters. This microscopic locking is what creates the macroscopic solid feel. Let's break down the two states of existence for this fluid. First, we have low shear stress, which results in liquid behavior. Because the movement is gentle, the slow movement allows water to flow around particles smoothly. As long as you are gentle, the network never locks up, feels like thick viscous liquid. Contrast that with high shear stress, which results in solid behavior. When you strike the fluid, that sudden force pushes particles together rapidly. The physics of the suspension means the water cannot escape. Particles jam and behave like solid. The liquid essentially runs out of time to flow. It is important to note the chemistry: a particle suspension. This is technically a colloidal suspension, not dissolved solution. In a solution, the particles would disappear into the solvent, but here they remain distinct. Specifically, the cornstarch particles, 5 to 20 microns in size, are the perfect size to create this jamming effect. Now let's look at the other side of the coin. Contrast: shear thinning fluids. In these materials, the viscosity decreases when stress applied to structure. A perfect example is house paint. Paint thins when stirred, thickens when still, which allows it to spread easily on a wall, but not drip down once the brush is removed. You likely interact with shear thinning examples every day without realizing it. Think about why ketchup needs hard shake to start flowing. You are applying stress to thin it. We see it in non-drip paint stays thick but thins when brushed. Even personal care items like toothpaste and polymer solutions flow when squeezed. This science saves lives through the application liquid body armor. Engineers have found ways where shear-thickening fluids incorporated into Kevlar vests for protection. The vest remains flexible for movement, but under bullet impact, STF instantly hardens, absorbing energy. We also see this technology in application traffic control. Modern engineering has created speed bumps use non-Newtonian materials for smart dampening. These smart bumps are soft when crossed slowly, stiffen when hit quickly, punishing speeders while rewarding safe drivers. For those who want to see the strange behavior in action, we have experimentation, the speaker experiment. By taking a sample of Oobleck placed on vibrating speaker cone at low frequency, we can see the physics visually. The rapid vibration causes solidification and bizarre moving structures that seem to dance on their own. Perhaps the most fun demonstration is experimentation, walking on Oobleck. It is possible to run across a pool of liquid, but it requires constant high-speed movement like running or jumping. If you hesitate, stopping causes hydroclusters to collapse and you sink immediately. We can visualize all these behaviors in summary, the viscosity curve. A Newtonian fluid is represented as a straight line, constant viscosity throughout. A shear-thickening fluid shows an upward curve with increasing shear rate. Finally, shear thinning is shown as a downward curve with decreasing viscosity. In conclusion, defying Newton, these fluids are more than just curiosities. They are crucial in material science. Their strange properties are explained by particle mechanics, proving that even simple kitchen ingredients demonstrate complex physics. In conclusion, these fluids remind us that nature is complex. By defying Newton, these materials have become crucial in modern materials science. Whether it is the shear thinning behavior of mayonnaise and blood, the danger of quicksand, or the protective power of liquid armor, we see that simple mechanics can explain complex phenomena. The next time you stir a sauce or squeeze a tube of toothpaste, remember, you are manipulating physics.